You're looking at a comet tail that seems to point the wrong way. Meet 3I Atlas, only the third interstellar visitor ever seen from Earth. Tonight we'll track it through our sky, explain why some images look wrong, and ask what this brief encounter tells us about how planets are made. No aliens, unless they show up with a DOI and a press kit. We'll keep it clear and cinematic. By the end, you'll know 3 natural reasons a tail can look sunward, what the carbon dioxide to water mix suggests about Atlas's birthplace, and why interstellar visitors are statistical gold for planetary science. If hyperbolic sounds like your group chat after midnight, don't worry, I'll translate. An interstellar visitor isn't bound to the sun. It drops in once and leaves forever. In 2017, one-eye Oumuamua passed by like a cryptic postcard. Small, dark, oddly shaped, and nudged a little more than gravity predicted, with no obvious coma. In 2019, 2I Borisov looked like a classic comet. Bright coma, familiar tail, chemistry screaming cold storage. Now we have 3I Atlas, named for a survey that finds asteroids and comets, not the Greek Titan. If it were the Titan, our thumbnail would have better biceps. These visitors are care packages from other stars. Young planetary systems play violent billiards. Some pieces get kicked out at escape speeds. When one swings through our backyard, sunlight turns it into a lab sample. Oumuamua showed how thin data can spark big debates. Borisov showed that interstellar can still look familiar. Atlas sits in between, recognizably cometary, yet sprinkled with frames that make people squint. That tension drives this story. First impression, comet, a hazy coma, an extended tail. Then a batch of images appears, where the brightest feature seems to angle back toward the sun. If you learned tails always point away, that feels wrong. Before we write science fiction, we check the boring knobs nature loves to twist. Perspective, rotation, particle sizes and charges, and the solar wind's shifting magnetic fields. Exotic answers are last resort. Chemistry matters too. Early hints of a high carbon dioxide to water ratio point to either a colder birth region around its home star, or a surface that's been processed by radiation and stellar winds. Borisov sounded frosty, yes, but no 2 visitors read the same recipe. Think regional cuisine, not a fast food franchise. Here's how tails actually happen. A comet's nucleus is a dark, lumpy snow dirt rock. Sunlight warms active patches, gas vents, gas drags dust. Fine dust feels radiation pressure and streams outward. Ionized gas couples to the solar wind and follows magnetic field lines. What we casually call the tail is really overlapping structures that change with time. A broad dust fan, 1 or more ion rays, and jet-driven spokes inside the coma. If a jet brightens and the spin lines it up with our view, the brightest feature can briefly look sunward. Physics didn't flip. The spotlight moved. Picture hair in the wind. Now add hairspray, spin slowly, and let a friend use a leaf blower from the side. Freeze the moment, and one strand looks like it argues with the breeze. Your hair didn't break fluid dynamics. The snapshot fooled you. 3 natural paths make the sunward look. First, directed jets plus rotation. Imagine a fixed nozzle on the nucleus. The comet spins, the nozzle sweeps a cone. A camera integrates for seconds. Geometry does the rest. A bright internal fan can look sunward while the bulk dust tail still points away. It isn't rebellion. It's a highlight stealing the scene. Second, mixed dust sizes and charges. Micron grains sprint under sunlight's push. Millimeter crumbs lag. Sunlight charges grains, so some feel magnetic deflection in the solar wind. Stack these paths in one photo, and your eye grabs the brightest slice, not the representative one. Eyeballs love drama, statistics do not. Third, solar wind geometry. Ion tails track magnetic field lines dragged out by the sun. The wind isn't a steady hairdryer. Sector boundaries, gusts, and tilts shove plasma one way while dust plods another. A still frame can mistake an ion ray for the tail and call it sunward. Physics is patient. Cameras are dramatic. Start patient. Walk through a simple case. Frame A looks classic. Sun to the right, dust fan opening left, a faint ion streamer leaning slightly. Frame B raises an eyebrow. Same geometry, but a bright spoke inside the coma lines toward the sun. The dust fan still opens left. The spoke steals the spotlight. A jet rotated into view and the exposure integrated that moment. You caught the comet mid-blink and decided it was sleepy forever. Frame C shows a solar wind swerve. Sun to the right, dust fan left, ion tail tilted upward after the magnetic sector changed. A long exposure emphasizes the ion ray. A short one favors the dust fan. Same comet, 3 moods. The physics didn't panic. The camera did. Still, images are gossip. Time series is testimony. Now, chemistry. Spectroscopy lets us eavesdrop. Sunlight excites molecules. They glow at specific wavelengths. Split that glow and count the fingerprints. Water and carbon dioxide freeze at different temperatures. A higher carbon dioxide fraction suggests ices formed farther from the home star's warmth, or that the surface was processed in a way that buries or depletes water ice while carbon dioxide vents when warmed. If comets are shaved ice, the CO2 to H2O ratio is the syrup recipe. Atlas says, "We're a cola town." Your local comet says, "Team Strawberry." But a ratio is a clue, not a verdict. We want spectra over time. Does carbon dioxide brighten before water as the comet warms? Do we see organic fragments that trace photochemistry? Does the mix change smoothly with distance from the sun? Watching the evolution separates birth conditions from weathering. When we say spectroscopy, we're really saying read the light like a barcode. Sunlight slams into the coma, molecules get excited, and then they relax by emitting photons at very specific wavelengths. Water photodissociates into OH. Carbon dioxide leaves its own fingerprints. Carbon monoxide, simple organics. Even sodium can show up with the right sensitivity. The grocery scanner metaphor works. The red line moves across, the pattern becomes numbers. Here, the pattern is in color, and the numbers become atoms and bonds. For comets, 3 levers matter: timing, ratios, context. Timing shows how outgassing responds as heliocentric distance changes. Ratios reveal the cocktail: water ice, carbon dioxide ice, carbon monoxide ice, and friends. Context, dust production, spin state, jet orientation, keeps us from overinterpreting a single spike. Imagine 3 consecutive nights. Night 1, a rising OH band announces water, while carbon dioxide is low. Night 2, both jump, but CO2 leads, hinting the surface layers vent carbon dioxide before water warms up. Night 3, water dominates and dust brightness climbs, saying grains are being dragged out more efficiently as gas flux increases. That sequence is a tiny biography of the top few centimeters of the nucleus. A nucleus is layered by history, pebbles stuck together in a disk. Some regions cold enough to keep delicate ices, others warmed enough to drive them off. Ultraviolet and cosmic rays baking the skin over millions of years. When a comet warms, it vents the part sunlight can reach, not the interior average. That's why evolution with distance beats a single snapshot. We also watch fragments, not just parents. Water is hard to see directly in the optical, but OH is bright. Carbon dioxide loves the infrared. Carbon monoxide helps untangle the story. Pair infrared spectra with optical photometry and polarization measurements, and molecules linked to grain sizes and textures. Fluffy fine grains scatter differently than compact larger ones. Polarization curves expose that. For an interstellar visitor like Atlas, a high CO2-H2O ratio can mean a far-out birthplace or a surface cold-trapped and later insulated. Distinguishing those needs patience. Do we see a late surge in water as deeper layers warm? Do organics brighten with CO2 or with H2O? Does the coma color get redder as dust production rises? Each answer nudges the origin story. And yes, there's noise. Air glow, telluric absorption, sky background, instrument throughput. The antidote is boring and effective. Repeat observations, careful calibrations, honest error bars. Spectroscopy doesn't reward hot takes. It rewards persistence. Interstellar visitors move fast, but our discipline stays the same. Measure, compare, repeat. If the sun only shone light, comet tails would be simple. But the sun breathes a wind of charged particles and drags out a magnetic field that twists into the Parker spiral as the sun rotates. That spiral is the stage where ion tails perform. Think of magnetic field lines as elastic rails. The solar wind flows along them, carrying the field outward. When a comet ionizes gas, those ions feel the Lorentz force and slide along the rails, making the ion tail. Now add structure. The sun's field isn't a polite bar magnet. It flips and folds. Sector boundaries sweep past like invisible weather fronts. Coronal mass ejections shove plasma into interplanetary space like slow-motion shockwaves. High-speed streams catch slower wind and form interaction regions. Each tilts, kinks, or brightens an ion tail. This is why still images trap us. Suppose a sector boundary crosses the comet's sun line overnight. The ion tail pivots a few degrees. The dust tail barely notices. A long exposure emphasizes the narrow, bright ion component. A short one favors the broad dust fan. If you don't label which tail you're admiring, you'll draw the wrong arrow and call the comet sunward. Nothing mystical happened. Plasma weather did. The Parker spiral also means geometry depends on where Earth is. Our sightline to the field lines changes as both Earth and comet move. Two observers a few thousand kilometers apart can record slightly different ion tail angles on the same night. That's not contradiction. It's parallax plus plasma. There's a practical habit you can build. When a dramatic frame makes the rounds, check space weather data for the date. Did a coronal mass ejection lift off 2 days earlier? Did the magnetic sector flip? Was proton flux elevated? Space weather records aren't only for satellite operators. They're part of the comet decoder ring. When the plasma context screams disturbance, an odd ion tail is the expected outcome, not an anomaly. Dust plays by different rules. Radiation pressure sorts grain sizes by push-to-mass ratio. Very fine grains accelerate away. Bigger grains lag and spread. Charging matters, but inertia dominates. That's why dust fans look broad and steady while ion tails look skinny and mercurial. In a composite, the human eye loves the skinny, bright thing and ignores the broad, pale one. The fix is simple. Annotate your frame. Draw the sun arrow. Mark the likely ion ray. Note the exposure time. It's not glamorous, but it keeps the physics honest. Visitors don't loiter. Atlas gives short windows where geometry is kind, brightness is merciful, and spectra are clean. We want light curves to time spin and flag jets, infrared spectra to read gas, and polarimetry to probe dust size and texture. Pros and amateurs can team up. A network of modest telescopes doing patient time series photometry beats a single giant mirror glancing once. Scientific fear of missing out hurts more than missing a sale. You don't lose $30. You lose a billion-year chemical history. Oumuamua taught that late is the enemy. Atlas is the reminder to set alarms and keep scopes warm. Could we intercept Atlas with a spacecraft today? Realistically, no. The velocity budget is harsh and the timetable unforgiving. But standby interceptors are on the drawing board. Vehicles loitering near Earth, ready to sprint when the next visitor is spotted. Think cosmic paramedics. Sirens optional. Sample return encouraged. Picture the sequence. A survey flags a new hyperbolic object. The interceptor pivots, burns hard, and commits to a fast flyby months later. On approach, it shoots long-range images to lock the orbit, then medium-range sequences to catch jets and dust fans, then high-cadence bursts to build a rotation curve. Minutes before closest approach, the dust analyzer warms, the mass spectrometer inhales, the polarimeter maps scattering in the inner coma. Then it's gone, coasting into emptiness, beaming down a hard drive full of context we never had before. What would we learn? We'd tie a dust-sized distribution to a gas composition at the same time and place. We'd see whether the bright fan that fooled our cameras is one active patch or a chorus of vents. We'd catch a temperature profile across the inner coma and compare it to the spectral lines we see from Earth. Most valuable, we'd calibrate the brightness of specific features to the mass they represent. Future images would stop being guesses and start being measurements. Could an interstellar visitor be engineered? To claim that, we'd need engineered signatures, narrowband radio, optical beacons, thrust patterns no sublimation can mimic, structures with repeating angles and exotic materials. So far, natural physics explains what we see with far less baggage. Will we ever capture one? The energy to slow a hyperbolic object into a bound orbit is brutal. But with stacked gravity assists and pre-positioned assets, a tiny shepherded fragment isn't impossible in the far future. One observation that would change the conversation tomorrow: high-signal in situ mass spectra paired with dust charges and sizes during a flyby. One clean pass grounds a decade of remote sensing. A second choice: a well-sampled, multi-wavelength light curve spanning weeks, tied to space weather logs. Spin, jets, chemistry, and plasma context in one dataset turns arguments into analysis. And yes, amateurs matter in that future. Coordinated photometry from different longitudes knits a near-continuous record. Small-scope polarimetry, even noisy, can catch trends that guide big instruments. The sky is big, windows are short, attention is scarce. A good network beats a lone hero. Line up the big three to see the pattern. Oumuamua was a geometry riddle with hints of non-gravitational push and no obvious coma. Borisov looked like the comet next door, but its chemistry sang in a colder register. Atlas looks cometary, with frames that invite misreads and chemistry that whispers chilly birthplace. Together they say ejection is common, disk chemistry varies, and comet comes in dialects. Expect rhymes, not copies. Clear a few myths. Sunward means artificial. No. Overlapping structures plus perspective and timing are enough. Extraordinary claims need extraordinary leftovers. Beacons, controlled thrust, telemetry. We don't have those. High carbon dioxide means ultra-far formation, case closed. Maybe. Or the surface was reprocessed. Time series spectra and thermal modeling decide. Interstellar objects should match our comets. Why would they? Different disks cook with different heat and stirring. One dramatic image beats a light curve. No. A light curve plus a sequence beats one viral still. If it's weird, it must be new physics. Physics is patient. Cameras are dramatic. You can read a weird image like a pro with 5 quick checks. Note the timestamp and space weather context. Did a magnetic sector flip or a coronal mass ejection pass? Mark where the sun is in the frame. Draw the arrow. Don't guess. Identify which structure dominates, dust fan or ion ray. Look for jet signatures that precess with rotation, repeating spokes or arcs, and ask for a data link. If the caption can't be bothered, neither should your credulity. Upgrade your feed from wow to how. Why care about a snowball from nowhere? Because each visitor is a probe we didn't launch. With enough of them, we can do demography. Distributions of spin, size, ice recipes, dust textures. Those feed models of planet formation and habitability. We start to measure how often disks build Earths, Neptunes, or deserts, and how often they fling leftovers into the dark. If you care about life in the universe, you care about the grocery list that stocked the kitchen. So where does 3i Atlas leave us? With a reminder that weird is what you get when light, dust, gas, spin, and plasma perform on the same stage. With a chemistry accent that hints at a colder upbringing, or a surface that remembers winter even as the sun warms it. With a checklist to carry into the next headline. Draw the sun arrow, label the tail you're admiring, check the wind, and ask for the data. The larger story is patience. Planet formation isn't a single plot twist. It's a statistic. 1 visitor is a clue. 3 is a rhyme. 10 becomes a pattern. 100 becomes a map. Somewhere on that map is the recipe that bakes worlds like ours. The recipe that bakes worlds unlike ours. And the long list of meals that never quite came together. Interstellar visitors are receipts from kitchens we may never see. We raid them while they fly by, and we add them to the ledger. Back to the headline. The tail that looks wrong is probably a bright jet aligned by rotation and camera angle, an ion structure shoved by the solar wind, or a dust mixture playing tricks with inertia and charge. The total dust flow still points away from the sun. The highlight steals the frame for a moment. That isn't cheating, that's lighting. Take 3 ideas with you. A sunward look can arise naturally from jets and rotation, mixed dust sizes and charges, and solar wind geometry. The carbon dioxide to water ratio hints at a cold birthplace or processed surface, enriching our dictionary of interstellar dialects. And the prize isn't a single headline. It's the statistics we build as more visitors arrive. So planet formation becomes something we measure, not guess. Stood next, we stay with 3i Atlas but change gears. Not the sunward optics, the case file. Surface versus sunlight. Color and polarization. Heat lag clocks, maybe a faint sodium whisper. Clues to what it is and where it was born. If you want mystery with measurements, subscribe to Night Sky Narratives and come back for the hunt. The night sky keeps secrets. We will ask better questions.